What if I told you that black holes don't actually exist? Not the way we think they do anyway. For a century, we've been mesmerized by these monsters. Regions of space-time so dense that gravity becomes a one-way door. Once you cross the event horizon, you're gone, crushed, erased from the universe. But as of today, a quiet earthquake rumbled through the world of theoretical physics. Three researchers dropped a bombshell. They proposed a new class of celestial object, a black hole mimicker. They gave it a genuinely striking name, the Conformalon. And if this theory holds water, everything we think we know about the edge of reality is about to change. To understand the Conformalon, we have to talk about symmetry, specifically a rule called conformal invariance. In physics, this rule says that the laws of the universe remains exactly the same, even if you stretch or warp space-time itself. It's like looking at a map and zooming in. The geometry stays consistent. Now the brilliant twist of this paper is that it asks a radical question. What if this stretching symmetry suddenly breaks? What if instead of a smooth, unbroken rule of nature, it just shatters when you approach a massive star? When that symmetry breaks, it doesn't create a singularity. It creates something far stranger. The researchers called it a conformalon. From the outside, a conformalon is a master of disguise. If you look at it from a safe distance, it has the exact same mass as a black hole. It curves space-time just like a black hole. It even has what it looks like an event horizon at the famous radius, the Schwarzschild radius. But here's the twist. That horizon, you can't cross it. Not because there's a physical wall, but because there's nothing. It simply isn't there. So imagine you're falling towards this object. You're accelerating, the gravity is immense. You expect to hit that point of no return in a few seconds, but you never do. According to the math, for a massive particle falling into Conformalon, it takes infinite proper time to reach that surface. The horizon recedes away from you. It's a cosmic mirage. You fall forever into an endless well that has no bottom. The matter in a collapsing star never actually forms a singularity. It just keeps falling and falling toward a surface it can never touch. And that's the ultimate tease of astrophysics. Now brace yourself, because this is where physics takes a head spin. You've heard of the gravitational redshift, right? It's the classic hallmark of a black hole. Light trying to escape the immense gravity gets stretched out. It loses energy. The wavelengths turn redder and redder until they fade into nothing. But a conformalon does the opposite. It exhibits a gravitational blueshift. Light emerging from near its surface doesn't get stretched. It gets compressed. The wavelength turns bluer, hotter, and more energetic. Imagine a flashlight trying to climb out of a gravity well, but instead of getting dimmer, it gets blindingly bright. This isn't just a weird quirk. This one detail is the key that unlocks two of the biggest knots in theoretical physics. In the 1970s, Stephen Hawking proved that black holes aren't entirely black. They emit radiation, they evaporate. But there was a catch, a massive headache for the Trans-Planckian problem. To calculate Hawking radiation, you have to trace the particles back in time to the event horizon. When you do this, the wavelengths of those particles become shorter than the Planck length. That's the smallest possible scale in the universe, a scale where our standard physics simply breaks down. We can't calculate that. It's a dead end. But watch what happens with Conformalon. Because the radiation here is blue shifted, not red shifted, these problematic ultra-high energy modes are never generated. The Trans-Planckian problem simply dissolves. It's like physics found a loophole. In a standard black hole, the Hawking temperature is positive. It radiates energy, gets smaller, and eventually pops out of existence. But when you run the numbers for a conformalon, the temperature flips, negative temperature. However, this negative temperature doesn't mean it's colder than absolute zero. In quantum physics, negative temperature means the system is highly energetic. It's an inverted state where the higher energy levels are filled. For a conformalin, this leads to a wild implication. It might have a maximum energy state. Instead of evaporating into a violent burst of infinite density, the conformalin could reach a stable final endpoint. The annihilation between infalling matter and the negative energy Hawking particles happens outside the horizon. It happens right in front of our telescopes, just unreachable enough to keep us guessing. And the holy grail of the conformalin comes with the black hole information paradox. Here's the problem. Quantum mechanics says information can never be destroyed. It's a sacred rule. But if you drop a book or a star into a black hole and the black hole evaporates, where does that information go? For 50 years, this has been the nightmare of physics. It pits Einstein against quantum mechanics. General relativity says the information is trapped. Quantum theory says it must survive. The conformalin may offer an answer. Because the collapse is singularity free, there's no breaking point. And because the process is mathematically unitary, information is preserved. In the conformalin framework, the matter falls forever, interacts with the outgoing radiation in a perfectly predictable way, and the quantum information is transferred back to the universe. No loss, no paradox, just a smooth, continuous transfer of quantum data. And if this is true, we live in a geodesically complete universe. That means you can trace any particle's path through space-time forever, past, present, and future. And you will never hit a dead end when the math stops working. No singularities, no infinities. And let's be honest, conformalins still face heavy hurdles. We don't know if conformal symmetry actually breaks this way in nature. We have no telescope powerful enough yet to tell the difference between true black hole and a conformalin. The differences are subtle. However, there is hope. Future gravitational wave detectors might pick up the unique ring-down structures, or perhaps the bizarre spectral shift of a blue-shifted horizon will give them away. Anyways, the conformalin, born from a mathematical quirk, a broken symmetry, stands as a testament to humanity's imagination. It asks us to look at the most extreme objects in the cosmos and reconsider. What if, instead of an abyss of destruction, a black hole is actually a doorway to forever? What if the universe is far kinder than we thought, preserving its secrets, preserving its information, and refusing to break under its own weight? Scientists gave us a new way to see the stars. We might never fall into a conformalin, but in our minds, we're already falling forever into the beauty of this unknown.